One, two, three, 1, 2, 3. Ladies and gentlemen, welcome. Welcome to a very special day at Optica. Today, on our online industry tutorial, it is Python Day. We have brought together something for the first time ever done live. We have a foundry on thin-film lithium niobate, and we have one of the leading tools on simulation of photonic integrated circuits working together to show you how we can simulate live, real life in front of you, a real life structure of thin-film lithium niobate photonic integrated circuit. The foundry is Luxtelligence, coming all the way from Saint-Sulpice in Switzerland. The leading simulation tool is Flexcompute, coming all the way from, well, it's a global tool, coming all the way from their offices in Boston. We're going to see something spectacular. Before I give them the floor, I would like to remind everyone that this is a very interactive session. And everything is open source today. The PDK of Luxtelligence is open source. So if you have any question about the layer stack, about the refractive index of any of the layers, about the losses, anything you can ask, because we are here to answer all the questions. Let's start. I hope everyone is ready. Today we have more than 400 people registered, and all of you after the event will have premium access to the tools that are going to be simulating today. But now let's start. And with this, I would like to first thank our sponsors today, Luxtelligence, and of course, Flexcompute. And then I would like to give the floor to one of the leading thin-film lithium niobate foundries worldwide, going all the way to Switzerland to meet Alberto Beccari. Alberto, thank you very much for being with us on Python Day at Optica. The floor and the attention of everyone is yours. Tell us a bit about Luxtelligence.
Thank you very much for the nice introduction, Jose. So yeah, as you rightly said, we are located in Saint-Sulpice in Switzerland. We are actually a spin-off of EPFL, as we'll see, and we offer all sorts of services related to the fabrication and validation of thin-film lithium niobate PICs. So we have a verified component library distributed through an open source PDK. We offer design support and design rule checking to make sure that the quality, to ensure quality of the designs that we will go on and fabricate for the customers. We conduct either multi-project wafer fabrications or custom runs where you can customize fully the stack. And we can do custom on-demand peak testing services with our in-house automated probers. So here's a zoom in showing exactly where we are located. We are on the coast of the beautiful Lac Léman in Lausanne, Switzerland. If you go to the next slide, we can see I would just wanted to show a brief reminder of the attractiveness of thin-film lithium niobate as a integrated photonics platform, why it's catching up speed, despite the fact that lithium niobate has been a workhorse of photonics for, I would say, since the 80s, the mid-80s at least. Now there's a resurgence going on because it's widely available in thin-film form, and it has this has a huge advantage in terms of efficiency of modulation, and it comes with all the qualities of the bulk platforms in terms of insertion loss and transparency band, which is much wider than for example, silicon photonics or indium phosphide photonics. So you can also design visible peaks. Also, it has some very attractive features. For example, you can have pure phase modulation without spurious amplitude modulation. You can build very, very low insertion loss components, very almost idealized in their photonic behavior. And of course, you can enjoy the state-of-the-art bandwidth and state-of-the-art modulation efficiency of the ferroelectric crystal. So if you want to fabricate a chip or a wafer run at the Luxtelligence, well, to start out, the easiest point of entry is using our open access PDK. A part of our PDK is open access. It's fully accessible if you visit our website following this QR code. And this is made for, it's really tailored to C-band operation. We have many building blocks for the C-band, and it's made for the Luxtelligence LPW runs, of which we have one just starting out now, and another one in June to follow, and more to come in the rest of the year. the turnaround is around 12 weeks, so very fast. We have a stack that is quite complete, but also rather simple, so we can give you some feedbacks and some prototypes already in 12 weeks. And here you can see a few highlights of the PDK. I want to emphasize just the extremely low optical propagation loss that is now comparable to the one of silicon nitride, for example, just not so distant. We also have good fiber coupling efficiency and, of course, very very fast Mach-Zehnder modulators, as everybody working with thin film lithium niobate wants. So now I guess, yeah, the question is now, if you want to realize a peak in thin film lithium niobate and use, for example, our process, how can you, you have to do some rather complicated electro-optical simulations, right? Simulate both microwave fields and the optical fields at the same time in the same type of structure. So for this, I give the word to Prashanta Kharel that will explain how you can do it with their fantastic tool.
Before you give the floor to Prashanta Kharel, this is a very interactive session, Alberto,
Oops.
and we are always looking forward to people to ask questions. We have Ronis Maximidis has the first question: can the VPI be reduced, and what is the minimum VPI value?
Yeah, good question, Ronis. Thanks. Yeah, well, the obvious way to reduce the VPI is by making longer modulators. Of course, you can. We have measured below VPIs below 2 volts without too much effort. Of course, there is a trade-off with the bandwidth there. So
Thank you very much.
the longer the modulator, yeah, let's keep it short.
Yes. So what is the length of the modulator that you measure for that you have for that 2 volts VPI?
Yeah, that would be around a little bit longer than 1 centimeter. So yeah, for 2 centimeters, you can typically be at the level of 1 volt.
Thank you very much, Alberto, and thank you for being here today. Your
You can also make
counterpart,
folded modulators if you have a limited footprint.
your counterpart today is Prashanta Kharel. Prash, thank you very much for arranging this tutorial, and tell us what's going to happen now. You're on mute. Prash, you're on mute.
Let me
Yes.
unmute myself. All right. Thanks, Jose, for the wonderful opportunity, and thanks everyone for joining. And we also want to thank Luxtelligence for providing us the Foundry perspective and also open sourcing your PDK so we can include it in tutorials like this. So before I start the live demo and tutorial, I wanted to give you a very high-level overview of thin film lithium niobate, a photonics platform, and really the simulation challenges that are associated with designing devices in lithium niobate. Lithium niobate, for its excellent optical properties, has gone from being like the workhorse of telecom industry to now leading a revolution in integrated photonics. We've come a long way from this demonstration that we did 5 years ago to show that thin film lithium niobate can actually be produced at scale using standard manufacturing processes. And today there's a growing ecosystem and a vibrant one of foundries and companies in this space. But if you want to design an active device in thin film lithium niobate, it does come with its own simulation needs and challenges. For example, let's just take a look at this active device in thin film lithium niobate. So this is a very compact electro-optic modulator that supports CMOS level driving voltages and larger than 60 gigahertz analog bandwidth. And you can already see, by looking at this device, that it involves multi-physics simulations, right? Involving optics, RF, thermal, which are inherently challenging. And of course, fabrication uncertainties always increases your project risk. But there are other unique challenges associated with thin film lithium niobate. The fact that the material is anisotropic means that the performance of your device depends on the rotation, right? Or how it's placed in your wafer. The index is close to 2, meaning devices are typically much larger in size than your typical silicon photonic devices, which also means that it requires longer simulation times. There are other tool challenges when you try to hop between optical and RF simulation tools. And it's also not trivial to go from component level simulations to system level simulations. And as you may already know, or maybe even experience, that these challenges are not just unique to thin film lithium niobate. Various optical, RF, thermal, and active device simulations, both at the component level and also at the module level, are really needed to design a real complex, real world photonic integrated circuit. So at Flexcompute, our vision is to provide you with a platform so you can run multi-physics simulations and do really fabrication-aware photonic design, so you can avoid costly tape-out errors, accelerate time to market for your products, and also reduce the development cost of integrated photonics. And towards that goal, we've released a number of simulation products. You're probably already familiar with Tidy3D solver, which is our GPU accelerated FTTD solver that uses both advanced algorithms and also fastest GPU clusters. And Tidy3D has been really a paradigm shift in how you do electromagnetic simulations. You know, I wish I had this tool back when I was designing devices in thin film lithium niobate. Unlike traditional approaches where you download a simulation tool and run it in your workstation or HPC cluster, with Tidy3D, you get to run the simulation of your choice using a workstation, and all you need is an internet connection to run very large electromagnetic simulations. We have a very nice Python interface and also a web interface that allows you to solve problems that are typically 100 to 1,000 times larger. Things are really fast because our code was written for, it's a GPU native solver, up to 500 times faster. And also, you know, you can run multiple concurrent jobs at the same time. And a tutorial like this would not have been possible if we didn't have a GPU accelerated solver like this. In a short 30-minute time, we're trying to redesign a device in lithium niobate. And building on top of Tidy3D and like heat solver and charge solver that we have released recently, we're also introducing PhotonForge, which is an end-to-end photonic design automation platform. So you can go from doing your component level simulations to really doing photonic circuit design and automation from a single unified interface. So there are a number of things that you can already do with PhotonForge. So it provides seamless integration with our GPU accelerated solvers. You can use Foundry PDKs through PhotonForge, and we have a growing number of foundries that we offer PDKs support for across very different material platforms. You can do circuit simulations, both frequency and time domain, and we also have a very powerful layout editor. And in today's tutorial, we'll use PhotonForge to demonstrate end-to-end active device design in thin film lithium niobate. We'll start by loading Luxtelligence PDK. We'll look at a few components. We'll run optical and RF simulations. We'll use those RF and optical simulations to calculate VPIL for an electro-optic modulator. We'll also design an RF taper so you can impedance match it to a 50 ohm source. We'll learn how to design a custom PDK component, in this case, a Y splitter. And then we'll put them all together using the schematic-driven layout and really make a chip that you can go and fabricate with Luxtelligence. With that, I'm going to now switch over to doing a quick demo of what our platform looks like. So
before that, and you know, Frash, this is an extremely interactive session. First question coming all the way to Alberto. What is the minimum bending radius of the TFLN platform Luxtelligence?
Right. Thanks, Pablo, for the question. In our MPW stack, you can have bands as tight as, let's say, 35 to 40 microns radius of curvature. We also demonstrated full edge cross sections, and there you can go down to 20 microns or even tighter.
Presh, another question for you. Do you provide access to cloud computing, or do people need to set their own?
No, we provide access to cloud computing. All you need is a web browser and account access, and you can log in from any web browser, even your cell phone, and start running simulations.
Please keep the questions coming, and now tell us about this directional coupler you have in front of us.
Beautiful. So the point of just quickly showing you our web interface is that, you know, you can basically run relatively complicated simulations directly from our web interface for running FTTD simulations. Like I was saying, we have other solvers, and we also have a web interface for PhotonForge, so you can do your entire circuit layout. It couples really nicely to our FTTD solver. But for today's tutorial, I'll switch over to Python and walk you through this workflow of how we can do end-to-end photonic active device design in PhotonForge. All right, if we don't have any questions, at least I'll start and we'll go through these 5 steps one by one, and we'll run everything live so you can see how fast the platform is. So to begin, I'll start by importing a Python library. So here we'll import Python library for Tidy3D. We'll also import Python library for PhotonForge. There are a couple of other PDK components that I'm loading here. In addition to our web GUI, where you have scripting capabilities, what we're also building is the ability to bring GUI more to the Python user. So here I'm going to also load a live viewer. Now, once you've loaded Tidy3D and PhotonForge, loading Luxtelligence PDK is as simple as loading another Python library. This is very similar to just saying import NumPy as NumPy, if you guys know that, a very famous Python library.
Prash, we need to be clarifying that this is an open source PDK. So
Exactly.
Everyone in the room have actually access to this PDK, and they can do this simulation themselves.
Absolutely. You can do pip install Luxtelligence, and you can use this PDK. Once you kind of import the PDK library, to load it, you just need to specify whether or not you want to include the substrate. And in this particular case, I'm going to just load the library with the substrate, because at some point we're going to be doing RF simulations. And in those situations, the substrate and also the cladding matters. Once you have loaded the technology, I can assign it as the default technology. And technology in PhotonForge basically specifies, what are all the layer stacks, right? So we can take a look at that. So you can see in Luxtelligence, thin film lithium niobate PDK, there are various GDS layers. And there's also, information about extrusions, like what are the thickness of each of these layers, how they sit on your wafer stack. And that all has already been incorporated when you load this PDK. So it's as simple as that. Once you do that, you can load your standard PDK components that Luxtelligence offers, and they have done all the hard work to design this device and make sure this gives you a very good, so in this case, it's a 1x2 MMI, and we can quickly check the performance of this splitter. And this is one of the powers of PhotonForge is once you've loaded a component, all you need to do is call S-matrix on that component, and it automatically runs a simulation for you and then tells you, okay, what is the performance of this device? You can quickly see that for the TE mode, it's about a 3 dB splitter. The TM mode, and this is kind of where you need to run a lot of these simulations for thin film lithium niobate, because the material is anisotropic, meaning that the refractive index for the TE and TM modes are not going to be the same, meaning the performance of this MMI is going to depend on whether or not you're using TE mode or TM mode as an output. In this particular case, we already ran the simulation and it was cached, so we can quickly see the results. We'll do some live simulations in the next few minutes. But there are other components, like directional couplers, edge couplers. They're all part of this PDK component that you can use and build your final circuit. There are active components like phase shifters, and you can see for active components, you not only have the optical ports, but you also see electrical ports. You have other components like electrical components, just like ground signal ground pads. And this is something that we're going to design later on to match it to a 50 ohm source. You can also have more complicated components that are made out of these base components, right? So you take these 1x2 MMI, you can take the electro-optic phase shifter, you can take these pads, and you can kind of string them together to make your circuit. In this case, it's an unbalanced MZI. And you can already see that a lot of these components out of the PDK are parametric in a sense that you can easily change, these components. And one thing that we built is this ability to visualize this not just in a Python notebook, but in your local browser. Let me just quickly open that. And you can inspect your components, and this should help you do a circuit layout in the future as well. All right. What's really unique about how we set up PhotonForge is that even though you made this complex component that uses all these base components, running getting a scattering matrix for this component is as simple again as calling S-matrix, and we'll look at that in a little bit. But it's also possible to visualize the cross section of this device. So in this case, I'm going to plot the cross section at x equals 0 for this unbalanced Mach center interferometer, you can see that there's this silicon substrate, there's the 4.7 micron thick box. You can see a very thin layer of thin film lithium niobate with waveguides defined in it. And then you see the transmission line, so ground, signal, ground, and then above the transmission line, you have air cladding. I'll pause here and see if there are any questions.
Lots of things, Prash. But first of all, let me say that this started really strong and we are really happy. Alberto, first question comes from you. Can you tell us if your platform is suitable to both C-band and O-band?
Yes, it's suitable to also to, well, the components are designed for C-band mostly, but they will operate also in the O-band with lower performance.
What is the total wavelength range of your platform, the total wavelength range from the minimal to the maximum?
The PDK is designed for the C-band, so in the around 50 nanometer plus minus 50 nanometers, let's say. But you can get a response, of course, at the O-band, and you can design your own components for the O-band. The stack supports it.
Another question for you, this 30 to 40 micrometer bending radius you mentioned before, is it for shallow or for deeply etched waveguides?
That's for shallow edge waveguides. We also have a second edge to define, to pattern the slab layer in the stack.
Prash, question for you. We are talking today about the open source PDK of Luxtelligence. Can we make our own PDK?
Absolutely. In fact, that we have a lot of nice tutorials in our documentation library. One of them, if you go to custom technology, we have really nice tutorials on how to make your own custom stack. And this is one of the things that we worked really hard so that it makes it very easy for you to build your own custom technology.
Another question for you, is it possible to specify the sidewall angle of the waveguide?
Absolutely, and that's a really good question, because let me quickly show you how this technology is built. If you look at the Luxtelligence LNOI, and in Python you have this nice feature in Jupyter Notebook where you can see this technology is parametric in a sense that right now the sidewall angle is 13.5 degrees. This was provided to us by Luxtelligence, for their Foundry process. But if this is different for your platform, you can definitely change that. And you can also kind of see it here that maybe not obvious, but you do have a sidewall angle in your waveguide.
Yeah, that's not obvious, but we believe you. Another question for you is, what is the best way to import a GDS design?
That's a really good question. Importing a GDS design is as simple as typing load GDS. We have a lot of, if you go to load layout, there's lots of examples on how to do this in our, we have really nice examples where we show that you can take a GDS file and just do load layout, and you can not only load your GDS file, if that GDS file is related to your technology stack, you can automatically detect ports and you can automatically add models, run simulations in just a few lines of code.
What is the format of the S parameters? Does it follow a certain standard?
Yeah, so we use touchstone format. So you can always export it in touchstone format, load experimental data and make models. So right now, for a lot of these simulations, I'm using tidy3D, meaning the FTTD simulation as a model, but you can also use experimental data for the models.
Is it easy? It is easy, very easy. Actually, I did it myself, Martin Otto, to import a GDS file. But is it possible to export the device's model simulated to a GDS file?
Absolutely. And in fact, that's what we're going to do at the end of this. We'll actually do an entire end-to-end design, and we'll export a GDS file that will be ready for fabrication.
That's all for now. Everyone keep the questions coming. Prash, let's calculate the VPI.
Awesome. Yeah, so now that we've kind of seen how to load, some of these PDK components, let's start and try to calculate a VPIL for one of these modulators. Well, you can define a geometry, but this PDK already comes with a number of different ports. By ports, those could be optical ports that are typically specified for your PDK, like in the case of Luxtelligence, a ridge waveguide with 1 micron width, and then you also have ridge waveguide with 3 microns width. And we can just take this port and export it to first to visualize what the cross section looks like, and then we can also build PDK components out of this. So in this case, I'm taking that port and I'm basically turning this into a straight waveguide, right? So this makes the process of building your circuits and routes very easy. But another really nice feature here is that we can take this port and convert it to a tidy 3D simulation in just one line. So here we're going to specify what frequency range you want to run the simulation. We'll specify that we do want to do group index calculation. This becomes very important in lithium niobate for velocity matching. So what you're trying to do for high-speed modulator design is that you're trying to match the group velocity for optics to that of the phase velocity of RF. And then I'm specifying that we do want group index calculation. Once I do that, in one line, meaning I just take the optical mode solver and run our mode solver through our cloud, and you'll see this happening live. We can see what this looks like in our web platform. You can see it's generated a full 3D cross section from just this 2D information about the port. That's because PhotonForge has all this information to go from 2D layout to 3D layout. The simulation is running, and in just a few seconds, it will automatically download the data, and then we'll be able to visualize the field profile for the optical mode.
Amazing.
So you can already see, right? So we solved for 5 different modes because it's a multi-mode waveguide because it's 3 microns wide. There are a number of modes. We can see there's a fundamental TE mode, and this is the TE1 mode. And you can see that the group index of this optical mode is around 2.21. So if you wanted to design a very high-speed modulator, you want to make sure that your RF index for the transmission line, the CPW transmission line, is actually very close to this. There are other limitations for bandwidth coming from the electrode loss itself, but one of the key criteria is to make sure your RF and optical signals are velocity matched. So this is why running the simulation is very important. All right, so we've run our optical simulation. Now I'm going to switch over to running RF simulations for the transmission line. But before I do that, do we have any questions?
Oh, of course, we have lots. So at any time, you let me know. The first one, we are seeing all the time that you are using regular cross-section shapes. How long would it take to measure something more complicated? Let's call something some irregular cross-sections.
Yeah, it's relatively straightforward. So let me I'm gonna keep going over to these documentation because this just shows you how we've so you can build any cross section. We call it custom port. You can make strip slot waveguide. So it's very simple to build more complicated geometries and also use them in your circuit. Once you have your ports, it's very easy to make routes or waveguides using those more complicated shapes.
More questions. After you load the GDS file, can you change the parameters in the GDS file? Can you edit the parameters of the GDS file?
So on the GDS file, you can add structures to it, but if it's not parametric, then you can't really modify for instance, the length of the GDS file, but you can add structures on top of it.
And one question, which I think is not a straightforward question, but how do the results of PhotonForge compare to numerical or console?
So that's a really good question. In fact, Tidy 3D, we've been around for many years, and we have benchmarked our solvers, of course, with other solvers. So that's not a problem, and we've also benchmarked it with actual simulation results. And so in terms of just matching our solver to other simulation solver, that's something that we do all the time before releasing any new things. So.
Is PhotonForge open source, or does it come with a Tidy 3D license?
PhotonForge is not open source. It is something that you would need a license for, and it's designed to help you go from Tidy 3D. So it needs a separate license than Tidy 3D.
Do you have any inbuilt optimizer in Tidy 3D? Also, if I want to use a Python package which is not ready in TidyCD, is it allowed to do?
Yes, so the Tidy3D front-end code or the Python API, in fact, that is open source. You should be able to see it. You can use it and add optimization on top. But there's also a design plugin within Tidy3D that allows you to do a lot of design optimization. They're really great tools for inverse design optimization as well. So Tidy3D offers a lot of optimization tools already, but you can also combine it with your own optimization tools.
There are many, many more questions. I will leave some of them for the next Q&A, but before I give you back the floor, Prash, Alberto, one question for you. What is the etching angle that Luxtelligence can realize?
Yeah, I think Prash showed it before when we examined the technology of the PDK. This is actually one of our strongest assets. It's quite close to vertical. We can have around 12-degree deviation from the vertical.
Right.
So.
Exactly.
Actually, that's pretty awesome, by the way, 12 degrees. Prash, let's continue. But there are a lot more questions waiting for you. And please, for everyone in the room, please keep them coming.
Beautiful.
Prash.
So yeah, so the next part, we've seen how to do optical simulations very quickly from PhotonForge, and it talks to our Tidy3D mode solver. Now we'll switch over and run some RF simulations. So for our RF simulations, we're going to consider the frequency range from 1 to 65 gigahertz. And for RF simulations, we do want to include the substrate, and because the RF modes are typically much larger than your optical mode, so you will see everything: lithium niobate, the oxide underneath it, the silicon substrate, also the air cladding, and that really affects the speed of RF signal in lithium niobate on an insulator platform. So earlier I showed you how you can just take the port information that comes as a part of the PDK and use that to basically run mode solver simulations. You don't need to follow that workflow. You can do more like a traditional workflow, right? So if you're used to making GDS files for your layout, so in this case, what I'm using is PhotonForge has layout capabilities as well. So it has, if you're used to open source packages like GDS Pi or GDS-TK, it has all the base geometry components. So in this case, I'm going to use 3 rectangles, one for the signal, one for the top ground, and one for the bottom ground, and add it on the transmission line layer for the PDK, so that all the GDS layers are all tracked properly. And then I'm going to use that to...
What parameters are you using to describe the transmission line?
So for now, so in this case, all you need to define is that what layer on the PDK it needs to be in. But of course, that layer is going to be associated with some material parameters. Like in the case of RF, we are associating that with some conductivity, some loss value. All that stuff is included as a part of the PDK's material library. So yeah, so I can make this a coplanar waveguide. Of course, this is a parametric component, so I can make it and I can change the length. Okay, so I'm going to make a 2 millimeter long transmission line, right? What I've done here is I've not only made this geometry, I've also actually detected the ports. And because this port information is in the PDK, we can see that we can automatically detect ports for this transmission line. We can visualize the cross section like before, but if you think about doing this VPIL calculation, what we need to make sure is that there is an optical waveguide in between these two electrodes. That's because the dielectric constant of thin film lithium niobate is pretty high. It's about 40, right? So it will actually affect the effective index of your microwave mode. And the fact that you have this high dielectric constant waveguide also means that the electric field is not going to be able to penetrate inside the waveguide as much. And this will also impact your electro-optic overlap and your VPIL. So to do that, what I'm basically doing here is I'm taking the CPW port, your ground signal ground port, and I'm combining that with 2 waveguide ports at these 2 different offsets. So I'm placing them right in between this gap. We can now inspect it. And like I was saying earlier, because this thin film lithium niobate, even though it's only a 400 nanometer thick slab, does affect the property of the coplanar waveguides. So I'm actually adding a mesh override to make sure I have at least 4 grid points in this thin film lithium niobate before I run my optical RF mode solver. Another thing we want to do when we start doing RF mode solving is that we also want to be able to calculate voltage across these transmission line. So I'm also adding an impedance calculator that we can later on use to do the line integral and calculate the voltage across this transmission line. All right. So we can, we can of course use our live viewer to visualize everything. You can look at various layers. Okay, so that's the metal layer. It's in layer 21.0. This is your slab layer, and this is also your ridge waveguide layer. Again, now it's to convert this to RF mode solver. It's one line. You just say your port, and you say convert to tidy3D and give it the range of frequencies that you're interested in. In this case, it's RF frequency. And this is also one of the very powerful things about PhotonForge is that you have one interface to run very different simulations. Traditionally, you would have to build this geometry all over in a different RF solver and rerun this computations. And oftentimes this is a very tedious process. So we have simplified this for you. So, so that in fact, the photonics looks very similar to RF. And this is also one of the things that we're trying to help bridge the gap for people who are in photonics so that they can run increasingly complex RF simulations. All right, so we'll convert this port to a mode solver, RF mode solver, and then we'll simply run the mode solver. And we can again visualize this.
And now we can see that the two waveguides.
Right, so you can see two waveguides, and you can also see the metal electrodes. And if you kind of look at the metal electrode, this is kind of what your earlier question was about. See if I can find. Oh, I'm on the RC version, so it doesn't show actually the material parameters here, but we're using the finite conductivity of gold here to run this to run this simulation.
While the mode solver is running, do you want to go through another quick set of questions?
Yeah, it's actually done, but
all right. Oh my God, I don't even have time with these cloud simulations. Oh my God, please continue.
We'll have a little bit of time when we run a batch of simulations in a little bit, but I'll just try to wrap this up here. So you saw that now we've simulated the electric field profile, and in this case, I'm plotting it at 1 gigahertz. So and we see that this is the right mode that we care about. It's antisymmetric. Once we've calculated the RF mode, we can easily compute the effective index of this RF mode. It's as simple as saying mgm data.n effective for mode index 0. We can also use that the impedance calculator that we defined earlier to calculate the impedance using this data, and then we can quickly plot it to see what that looks like. You can see that from this simulation, we see that the close to 65 gigahertz, the impedance is around 55 ohms, and the effective index of the microwave transmission line is around 1.87. Now, this is a measured data from Luxtelligence, and we're very grateful that they provided us this measurement data, and we see that what we simulated matches very closely with what they measured, and the error in the microwave index is less than 2%, and then the error in the impedance is less than 5%. So this is really good results. All right, so but what this is also showing us is that there's a lot of room here to optimize the microwave electrode, maybe by adding capacitively loading the transmission line, so you can turn this GSG electrode into a slow wave electrode, so that you can increase the effective index and then velocity match with RF. And those are the types of simulations, 3D simulations, we will be adding on our documentation page soon. All right, so I'll pause here and before I do the overlap integral to calculate V pi, do we have any questions?
No, you cannot imagine, Prash, how many. But the first one, I'm gonna go to Alberto. Alberto, what's the thin film stack that we're using in these simulations?
Yeah, right. Maybe I can share the screen. I'm sure I have a nice illustration here.
Yeah.
If you can you share quickly?
Yeah.
Prash? Thank you very much. All right. You should be able to
I
see
don't
my
know
screen.
about you
Yeah.
guys, but I'm enjoying this tutorial a lot. I have goosebumps, by the way. Please continue, Alberto. You can share your screen now.
Yeah, so I think you see it now. This is the stack that we use
I don't
for the
see it yet.
simulations. Ah,
Not
oops,
here.
excuse me. No, I didn't select it yet. Right. Shared. That should work. So yeah, the stack looks like this. As we mentioned before, it's partial etching of lithium LNOI. Lithium niobate is originally, the thin film is 400 nanometer. For this PDK, it's partially etched down to 200 nanometers. So we have a 200 nanometer slab residual, and the ridge waveguides have a sidewall angle of about 12 degrees or 78 degrees, if you want to see it the other way. And we have buffered electrodes, so that means that they're separated from the slab by some oxide layer that's about 1 micron thick. And we have gold electrodes on top.
Thank you very much, Alberto. Back to you, Prash. People really like the approach and the gear. One of the questions that's coming a lot is, can you run the software locally on the HPC cluster? And if so, is there a different licensing instead of using the flex coins?
Yeah, the short answer is yes, you can run it on your own, but you do need your own GPU cluster. That's not the standard approach, because we do want users to leverage our cloud compute capabilities because you don't need to manage all the HPC clusters. But if that's if that's something that you are interested in, please feel free to reach out to us.
I
That's
strongly recommend everyone to use the cloud computing process of Flexcompute, because what you are seeing here is pretty spectacular today. How fast the simulations are. What is the biggest peak, the biggest photonic integrated circuit you can simulate in your servers?
So it really depends. With PhotonForge, you can really scale to centimeter scale circuits, because what you end up doing is you end up simulating your individual components, and then once the individual components are run, you can simulate the entire circuit. But regarding Tidy3D, in Tidy3D, you can scale to pretty large problems. I think if you think in terms of like the number of grid points for your simulation domain, I think we can easily scale to 20 billion grid points. I think we've run simulations that are even larger. I think up to 50 billion grid cells. But much larger than what you could traditionally simulate in a reasonable amount of time, without not taking it days or weeks to run those simulations.
Then questions keep recurring. I'm trying to compile the questions in group. Is it possible to do clipping of the GDS file after you load it?
Absolutely. Yeah, we can definitely do that.
Another question is if you could say about comparison or potential collaboration with the IPKs from Lucida.
So PhotonForge can do a lot of the circuit level simulations. I think we do collaborate with Lucida and IPKIS in terms of integration with Tidy3D solver. Our goal with our individual solvers is to also offer integrations with other platforms, not just IPKIS, but GDS Factory and other players who that want to kind of interface with our solvers. PhotonForge is just our version so that we can offer this seamless interface, because we do have a lot of other solvers that we're working in parallel, and it's just easier for us to build this integration.
A lot of people are complimenting you for the speed of the simulations. One question I keep recurring is, are you using different mode solvers for RF and photonics?
In this case, no, but there are certainly differences. There are a lot of things that you have to implement on top of your traditional optical solver so that it works for the RF. But
there is a lot of questions about group velocity, but because we practiced yesterday that this is coming, I'm not going to answer that. I lead you back the floor. There are more questions waiting for you, but please, I would like to ask everyone to keep them coming. Back to you, Prash.
Beautiful. All right, so what we did so far is we saw how to run optical simulations and calculate the mode profiles. We also saw how to run RF simulations, calculate the mode profile, but also calculate impedance and index of your transmission lines. And so now we're going to take those two data, so the optical simulation and RF simulation, and then we're going to use that to calculate the V-pi-L for this modulator. Now, you know, the thin film lithium niobate is a great material because it has pretty large Pockels effect. And the Pockels effect is, you know, when you apply electric field on thin film lithium niobate, you actually get a refractive index change. The dominant tensor component is this R33 component. And then, you know, what we're looking at is the electric field in the Z crystalline axis. If you once you've calculated the electric field, we do need to normalize it, and this is why we had that voltage line integral set up. So we see that for this mode solver, the voltage across the transmission line is about 11 volts, and you can use this to normalize your electric field. Once you have this electric field and you know these constants, material constants, we're now able to calculate the change in index for the waveguide, and then we can use that to essentially calculate V-pi-L. So I'm just going to run through this this calculation. I'll walk you through what this function is essentially doing. It's looking at the voltage applied across the signal and ground. It's converting the RF field, normalizing it, and then it's basically recentering the RF field and optical field, and then doing an overlap to calculate the effective the refractive index change along the waveguide. Now, one thing I wanted to kind of point out quickly is that this is why you need to really do RF simulations, right? So if you think in this coplanar waveguide, you have 4 microns gap, and let's say if you were to be applying 1 volt, you would expect the electric field in this gap region to be around 2 e to the power 5 volts per meter. And you can kind of see that from this RF simulation. You see that right where the electrodes are, the field is 2 e to the power 5. But if you look at where the waveguide is, where the thin film lithium niobate waveguide is, the field strength is a lot lower, right? So it's closer to, you know, it's actually, you know, we calculated this, what this is. On average, it's around, it's 8.8 times 10 to the power 4. So there's this reduction in electric field because this is a high dielectric constant material, and this is also what leads to reduced V-pi-L. And this is why you need to design your electrodes and where you place them and how wide the waveguide is and all this stuff, so that you can get to you know, low V-pi-L for your modulators. From the simulations, from doing this electro-optic overlap, we see that the V-pi-L for push-pull configuration in an MZM is around 2.9 volts per centimeter. But we do need to account the input reflections and also do the voltage scaling, because the impedance, as we saw, close to 1 gigahertz is not 50 ohms, right? So it's a little bit higher than that. And once we take into account, we see that the simulated V-pi-L is close to 3.3, and this is a measured data from Luxtelligence, and what they measure is that the V-pi-L is around 3.4 volts centimeter. So there's also a great agreement between simulation and measurements. All right, so I'll switch over. I'll run some batch simulations here, and we'll have a few minutes to discuss or take in some more questions. So for the next part of this design, what we're going to do is we're going to try to see if we can redesign the CPW pads so that we can impedance match it to a 50 ohm source. We saw that the electrode was around 55 ohms. So how do we make sure that we match at least the pads to 50 ohm? Well, one of the things you could do is we can just change the so if you look at the CPW pad, we can essentially change the gap here to change the capacitance, and then that would actually, and that's one way we can use to impedance match. So the design goal here is we're going to change the electrode gap, and we're going to try to match it to 50 ohms. And in Tidy3D, and what we can do is we can run a batch of simulations. So here, what I'm doing is I'm basically creating a function that returns a mode solver, the RF mode solver, as a function of gap. And then I'm just creating a list of mode solvers where I vary the gap. And then I just run a batch of simulations. So these simulations are now getting sent to our servers, and we have maybe a minute or two to take in a few more questions while the results come back.
All right, so you want to go through the questions now. The first one, can you define the V pi times L alpha, let's say as function of constants height, and optimize the parameter?
I missed what as a function of, sorry, what?
Can you define V pi times L first and then optimize it?
Yes, absolutely. So you can, that's a really good question. So essentially, everything I did here, I'm just running it through it once, right? But what you can do is you can essentially turn this into a function, because these are just Python functions. And you can turn this into an optimization loop where you have some goal of, okay, I'm going to change the thickness of the metal. I'm going to change the gap of the metal. I'm going to change the width of the waveguide, and then run these simulations to see how that impacts VPIL. So yeah, that's definitely possible.
A few questions are asking about if you are doing 2D or 3D simulations.
Right now, the mode solver simulations are 2D. Just like, when you try to run FTTD simulations, you might want to do a 2D mode solver and launch that. We'll also have 3D simulations both for optics and RF, and we'll release those notebooks soon.
Do you have system characterization capability for the photonic integrated circuit, Alberto? Alberto, they're asking you if you have you are actually in your foundry. Do you have system characterization capabilities for the photonic integrated circuits?
It's for well, yes. It's for the Foundry. Okay. For a moment, I thought it was more about system simulation with PhotonForge. Yeah, for sure. We have characterized and optimized all the building blocks that you see released in the PDK by building
What is the
photonic circuits
fastest
and
modulator
characterizing
you
that.
have measured? What is the fastest modulator you have measured?
Well, we measured well beyond 70 gigahertz modulation bandwidth, but more or less limited by our RF equipment.
And Andrew Prash is asking, how does PhotonForge handle structure electrodes whose cross-section varies down the propagation length?
That's right. So for those, you would have to run the full 3D simulations, and we'll release some notebooks to show you how to do that.
One more question and then we continue. Is the software able to do bandwidth simulations? Let's say determine the velocity mismatch between the RF and the optical phase velocity and the associated 3D bandwidth.
That's right. In fact, we do have another notebook example that shows you how to simulate the electro-optic bandwidth. Not just that, you can actually take that response, electro-optic response of bandwidth, and run a full time domain simulation to see what the eye diagram looks like, and really do system level analysis. So yeah, that is also possible.
There are possibly 100 questions that I'm not going through. You're going to get all the questions, but the main question here, Prash, the one that everybody is asking, are they going to have access to all the information you are sharing today?
That's right. Yeah. So please, like I said earlier, please contact us, and we would be at my email, so prosh@flexcompute.com, or you can also contact info@flexcompute.com. So you can contact any one of us, and we'll be happy to share these notebooks with you. You can also check out our documentation page. But yeah, we'll be more than happy to send you this information.
Back to you.
Awesome. All right, so we've seen how, so we ran a batch of mode solver simulations where we're just sweeping gap for that CPW, and we see that, okay, if you were to make the gap around 58 ohms, you actually get a perfect 50 ohms CPW pad. So we're going to actually use this CPW pad to later on build our own circuit. All right, for now, let's quickly switch over to doing an optical component design. So you might have a bunch of components from your PDK, but oftentimes you will need to design your own PDK component. So in this case, let's say I wanted to design a Y splitter with a simple S-band geometry rather than using MMIs. Again, I'm going to switch over to the optical technology where I just remove the substrate, and this helps me reduce the size of simulation. You can use geometry primitives in PhotonForge, like S-bend and path, and you can also make sure your designs are fabrication ready. So if you don't want any designs that are smaller than 100 nanometers, you can make sure that that's incorporated. Once I do this, once I make my parametric Y-splitter component, I can easily detect ports and I can add a tidy 3D model. It's just, few lines of code. And what I've now made is a component that's a Y-splitter component. And I can actually run this simulation. Let me run it so for some arbitrary, parameters. And if I were to run this simulation, so again, running simulation is as simple as just calling S matrix. I've added a few things like I want a field, a monitor in the XY plane here. And let's quickly run the simulation. And as you can see, when I went from creating this P cell for this Y splitter to running a tidy 3D simulation in just a few lines of code. And PhotonForge automatically builds this 3D geometry from these 2D layouts because it can look at that technology file and know what all the materials are, where to put the sources and monitors and all that stuff. This should be done in a few seconds, and we'll look at the S matrix and then see if we need to change our design and optimize it further. Maybe we can take in one or two questions.
The question is for the next one. It's going to be for Alberto. Just to keep switching. Do you have other components like detectors that match the speed of your modulators, Alberto?
No, at the moment we're not supporting detectors.
Awesome. All right, so the simulation is complete, and now it's downloading the data. And oh, I think I added a D here. Okay, so you can clearly see that there's added loss on this splitter. We can even visualize that. Okay, you can see there's a ton of radiation loss because this bend is too tight, right? So I can go back and readjust this thing. In this particular case, I've already run this simulation, so it should be cached. And we'll see that, okay, now we're getting closer to a perfect 50-50 splitter. But you see how quickly we can do a component design. And this particular component would now be a part of your own custom PDK library that you can use to build your own circuit. Now that's what we're going to see at this, maybe in the last few minutes. We can take all these components. So in this case, this GSG pad that we designed, we can take the Mach-Zehnder modulator arms. And this is kind of what I meant by schematic driven layout. So you can actually take your components and just take instances or you can take multiple of those. So take a Y splitter for input, Y splitter for output. You can take your MZM arms. You can make these tapers to transition from 1 micron waveguide to 3 micron waveguide. And you can simply just connect them, like specifying, okay, I want to connect the port 0 of the input taper to port 1 of the input Y splitter. And you can define a circuit model. So later on, PhotonForge will know how to exactly compute the S matrix for this entire circuit without you doing any extra work. And you can also, you can make increasingly complex device. So this is just an MZM Mach-Zehnder modulator. You can add an edge coupler. Everything is parametric, so you can, change the angle for, and then you can combine all of this into a full chip layout, right? So where I'm adding, multiple of these Mach-Zehnder modulator, in this case 3. I mean, we can add 5 if we wanted to pack in a lot of modulators there. You can add text labels. So this is just like your standard, how you do GDS layout. And then this is what we talked about earlier. I want to show you. I want to show how. Just a second. Maybe in the right folder here. Yeah. So we can run this, and it generates the GDS file that you can use to take this GDS file and give it to Luxtelligence, and they should be able to build this chip for you. And we can also visualize all these things in our web platform. So I'll stop here and